So, initial and boundary value problems. So we've talked about initial value problems, but it turns out that when you have a higher order differential equation, there's a possibility for a boundary value problem where they give you information about boundaries instead of just what's happening at the initial part. We're going to focus more on initial values. We are going to talk about boundary value problems. You guys are going to do some examples with boundary value problems. But hopefully it won't come up on the test. I don't know, it might. Yeah, well, So let's first focus on initial value problems. Maybe I should cross out boundary values for now. And let's focus on initial value problems. So an nth order differential equation that has an initial condition would be, the order, right? It's the highest derivative you have. We're going to stick with linear differential equations just to make things easier for ourselves. So a linear differential equation, an nth order initial value problem would be a differential equation that has the nth derivative of something as the largest derivative. And it's linear, so the y's and all the derivatives of y's are not being squared or square rooted or taken the logarithm or a sine or trig function of. Now the x's, your independent variables, can be anything. It can be sine x or cosine x or ln x or any of those weird things, but the y's themselves are not taken to those special functions. Now, in the first order, we only had one initial condition. But if you have an nth order differential equation, you should be looking for n initial conditions. And the initial conditions are generally based on one point. I don't know why this is to power here. It's based on one point, say x naught. And we're finding values for the original problem, the derivative, the second derivative, as many derivatives as one less of the order. So if you have a second order differential equation, your initial conditions will be made up of the function evaluated at the point, the initial point, and then the first derivative evaluated at the initial point. Okay, so a second order differential equation will have two initial conditions. Starting with the original function up to the first derivative, but not including the second derivative. Now there's a theorem that we're not going to prove, because we never do, about the existence and uniqueness of an initial value problem. And this says that if you have an initial value problem with the appropriate parameters, like an nth order differential equation will have n minus 1 initial conditions, then you're guaranteed to have one unique solution for your problem. Sometimes you're not guaranteed to even get a solution, and we'll see that for boundary value problems, you might not get a non-trivial solution or whatever. But if you have an initial value problem set up like this, then you're guaranteed one solution. Exactly one. That's the uniqueness part. So the existence part means you're guaranteed a solution. The uniqueness part says that you have one and exactly one solution. Well, if you don't have an initial value, then your solutions would just be general curves, right? So 2-parameter family of curves, 3-parameter family. So this uniqueness in existence theorem is based on your initial conditions. And like before, you're guaranteed a solution within some interval. It may not be all of real numbers, but then, we probably don't need solution to all real numbers. We only need a solution up to from 0 to 15 or something. Some shorter interval that we're looking at. Okay. So let's take a look at a problem that might have something just to get us introduced to higher order differential equations. I only have one problem here. It says 1 through 4. So here we're given a family of solutions. So this would be your, quote, general solution. So given a family of solutions, general solution for the differential equation in the indicated interval, find a member of the family that's the solution to the initial value problem. So our initial value problem consists of a differential equation and enough initial conditions that would make it an IVP. So this is a second order differential equation. We should have two initial conditions. Yeah. Yeah, I was thinking about that. Okay. Yeah. You should check, but in the problems that you're given, you're probably going to have enough. It's just that when you don't, then you're not guaranteed a solution. And so if you notice the solution itself, the solution is a family of solutions, and your solution has two parts to it, and it has two arbitrary constants, C1 and C2. Right. So IVP is an initial value problem. It has, so these are the ICs, initial conditions, and this is your differential equation. So the IVP is the set that has a differential equation and the initial conditions. And in the past, we've only had one initial condition, and that was because we had first order differential equations. Higher orders will have more initial conditions. All right, so we have a two-parameter family of curves. We should be able to solve for this to get our one unique solution. And it looks like this is going to be for all real numbers. So let's see if we can work this out or find a solution or find a unique solution. So we have our y. We're going to need the second derivative according to this differential equation. So we're going to use this to solve for the arbitrary constants, because that's what we use the initial conditions for, right? Solve for the arbitrary constants. So we need the derivative. Derivative e to the x is e to the x, and the derivative of e to the negative x is negative e to the negative x. So we want to get to our second derivative. And we want to put that into our equation. Oh, wait, that's the check. How are we going to solve for this? Oh. Yeah, we can use it to check to solve the equation. That was a problem that I would normally have put on the first exam, and I took it out this year, this semester. Yeah. So anyways, we're solving for the arbitrary constants. Let's put 0 in for y. Y of 0 is supposed to be equal to 0, but this is your y function here. So let's put 0 in for x. So we get c1 plus c2 is equal to 0, right? And then our first derivative evaluated at the initial point is going to be equal to 1. And the first derivative is this expression, so there's a negative sign. And then you can do whatever you got to do to solve for this, and these are most likely going to be linear because we're dealing with linear differential equations. So you can use linear algebra or just regular algebra, I suppose. I think it's 1/2 and negative 1/2. So your solution, your one unique solution that exists is going to be 1/2 e to the x minus 1/2 e to the negative x. And that does exist for all real numbers, so we're all good. Okay? Yeah. Because of the theorem. The idea is that if you try to come up with another solution that you think might be right, it's not going to work. So there's no other solutions that would work for this. Yes. Initial value problem. Okay. All right. So that's our warm up. Let's take a peek at what a boundary problem would look like. Boundary value problem would look like. Here's an example of a boundary value problem, and the main thing about showing you this is to try to see what the difference is between a boundary value problem versus an initial condition or initial value problem. So a boundary value problem could look like this. We have a regular linear differential equation. In this particular example, it's a second order differential equation. And then here are our conditions. So the condition is based on y of a is equal to some value, and then y of b is equal to another value. So notice the difference between something like this versus an initial condition. Initial condition focuses on one particular x value, and it gives a y value and a y prime value. This one has two x values, a and b. And so it kind of makes sense that this is a boundary value problem because your conditions are based on a boundary. Two different values, a and b, and then it's giving you the y value of that. Yeah. Though that's a little bit different. That's the mean value problem, mean value theorem, which is different from what we're doing here because that's only looking at the first derivative, right? But it's not an initial value because now you're looking at another value here, and if you remember, if your mean value theorem could be a lot of different answers, right? So it doesn't guarantee that you're going to get one unique solution. All right. So the main point here is that the boundary value problem does not guarantee you a unique solution. You might find a solution, but then there might be 3 other solutions that would work, or you might not find a solution at all. The other boundary conditions might look like a combination of the original function and the derivative evaluated at the endpoints, at the boundaries. I guess we'll call them boundaries because it makes a little bit more sense calling them boundaries. Yeah. Yeah. It doesn't really matter. I mean, we could just switch the B and the A, but it's better to think about it that way. That the A is smaller than the B. But the point is that they're different. A is different from B. Yeah, well, that's the other thing is that for the boundary, for the initial condition, initial value problem, you tend to look for the largest interval where it would work. For the boundary value problem, all you're going to say is that you're concerned about what's happening between A and B, and you don't care what happens outside of that. Yeah. All right, let's take a look at maybe an example. Is there an example here? Oh, there's 4 parts to this. Oh, let's just do 1 or 2. So here we have our differential equation that has our general solution, a 2-parameter family solution. We'll call that a general solution, and determine whether the member of the family can be found that satisfies a boundary condition. So let's take a look at a couple of them. Let's take a look at, I don't know, A and C or something. So let's see if we can find a solution for our first one. So notice that the boundaries between 0 and pi, your boundaries are 0 and pi. So you're focused on the interval between 0 and pi. Now they say it goes off from negative infinity to positive infinity, but that part doesn't really matter because if you're solving for this, then you really generally just care about what happens inside. So we have y and y prime is given to us here. So we generally just want to set this up as I'm going to put the 1 on the left side this time. So 1 is equal to y of 0, which is equal to the y function evaluated at 0. So that's c1 e to the 0 cosine of 0 plus c2 e to the 0 sine of 0. So 1 is equal to, what's cosine of 0? 1. So that's going to stay c1. What's sine of 0? This is 0. So c1 is equal to 1. Oh, we need the derivative. Y prime is equal to, looks like we have a couple of product rules. C1, e to the x cosine x plus e to the x, derivative cosine, negative sine. C2, we have e to the x sine x plus e to the x cosine x. All right. So we want our derivative, our y prime, evaluated at pi, and this has to equal to 0. So we need to, I don't want to write everything out, so I'm just going to have to ask you what's cosine of pi? 0 or negative 1? It's negative 1 plus sine of pi. So I'm just going to put 0 for that one. And then now C2, sine of pi is 0 again, and cosine of pi is -1. So this is a negative e to the pi. All right, well, what do we have? We have C1, by the way, was equal to 1 already. We've established that. We found that already. So this is going to be 0 equals negative e to the pi plus C2 negative e to the pi. And so C2 is also going to equal to 1, or is it -1? -1. Say it again. Oh, we solved for C1 from the first equation here. And so I made that into a 1. Is this okay? Yeah. All right, so we have C1 is equal to 1, C2 is equal to -1. So we do have a solution for this. Yeah, well, in this case, this interval happens to work for all real numbers. But like I said, in general, we tend to just care about what's happening between the boundaries. Otherwise, you're kind of extrapolating, which sometimes it's a good thing, sometimes it's not. T2 is positive 1? Do we want to agree it's positive 1? I mean, I maybe might have done something wrong here. What? It's just a sign. Like a B plus versus a B minus. It's just a sign. Just a sign. Well, I don't know. Should we change it? That's right. I don't know, Josh. Whatever. What? It is -1? It is positive 1? So if you do, then it would still, this would be both positive, and you bring the other one to the other side, it'll be negative, right? Yeah, so it is. I think it is. You just messing with me or what? Oh, okay. All right. Hope it's right. Let's do D. I'm trying to find one that's not going to work. Let's see if this one works or not work. Does not work. Let's try. So this one is just y's, so we don't have to take the derivatives. Or we already have the derivative, but we don't have to mess with the derivative. So these just are looking at the original functions. So we have y of 0, c e to the, what's cosine of 0? Cosine of 0 is 1, and sine of 0 is 0. So in this case, c1 is equal to 0, right? And y of pi is c1 e to the pi. Cosine of pi again is -1. And sine of pi and this is supposed to equal to 0 also. So here we have C1 is 0, right? So we have information about C1, but we don't know anything about C2. C2, that might mean C2 could be anything. But the point is that we don't have a unique solution for this. It looks like we can use anything for C2. It looks like we can put, let's C2 equal to 0, it should work. C2 is equal to 5, it should work. C2 is equal to -3, it should work. It looks like we could put anything for C2 and it would work. So I think we have a solution, but the solution is not unique. This is a solution, and I believe it's unique based on these boundary values. Yes. How do we know? We can try to find another solution and see that it won't work. Oh, we don't have a solution. I mean, we can have C1 is equal to 0, and then C2 can be anything, and then it should work, it seems like. So, seems like we can just say no unique solution. We'll say y is equal to, so C1 has to be equal to 0, so that just means we have C2 e to the x sine x would be our solution. But then since C2 can be anything, that's an infinite number of solutions that we can have. Okay. Free variable, yeah. Because we tried solving for C1 and C2, we found that C1 is equal to 0 in both cases, and we didn't see any restrictions on C2. So it seems like we can put whatever we want for C2 and it'll work. So we got, yeah. It satisfies the differential equation. This is a solution for a differential equation. It satisfies that. It satisfies these conditions, these boundary conditions, because that's what we were doing. Uh, oh, okay. So if that's the question, then it looks like the answer is yes. I wasn't looking at the question. I was just trying to find one where we found a non-unique solution, or maybe there's one here where the solution doesn't even exist. Well, not that it won't exist. So I'm looking at this thing, it's equal to 0. So y is equal to 0 would be a solution for this. But it's like a degenerate solution because it's called a trivial solution. So if you just have the trivial solution, then there's nothing else interesting to look at here. And that might have been the case for one of these other two that we didn't do. So a lot of weird things can happen if you're looking at boundary value problems. Not a lot, just a couple of things. That's not a unique solution. If this is non-zero, then it could be possible that your boundary condition is not going to give you 0. Then maybe you won't get a solution at all. If you're, yeah, I guess so. Two parameters that indicate, determine whether a member of the family can be found that satisfies the boundary condition. Oh, I don't know. These things might not. I don't know. Oh, the pi over 2. because that one goes makes one of them equal to 1 and the other one equal to 0, and so it's possible. Let's see. I guess we're doing another one. Oh, we don't have any more room. All right, let's see. Y of 0 is equal to 1. So y of 0 is equal to cosine of 0 is 1, right? So this is c1 e to the 0 cosine of 0 plus 0, and that's supposed to equal to 1. Our second boundary condition, y of pi over 2. So cosine of pi over 2 is 0. So this is 0 plus c2 times 1. c2 times pi over 2. That's equal to 1. Yeah, it looks like we're going to get a solution here too. Yeah. Y of pi. Something like that. That might give you something. So in any case, other things can happen. Yeah. Um, oh, they're just saying that this is a solution to that. So if we want to, we could take this function, take the derivative and the second derivative and plug it in here to make sure it does work. So they just gave us the differential equation for context. Yeah. General solution. Because that's how boundary value problems, that's how boundary conditions are. The boundary conditions don't have to be y and y prime. It could be y and y, or it could be y prime and y prime. And that's the thing about the boundary conditions, that it's telling you something about the boundary and not necessarily the derivatives of the function. So here in this boundary value problem on the first one, we had something about y prime, but in the rest, we didn't have anything about y prime. So that just means that these are looking at the boundaries themselves. And according to our example of boundary value conditions, you can have a boundary value condition that's just about the function itself, or just about the derivative itself, or a combination of the function and the derivative. And that's just how it's given. Because you have a two-parameter family of curves, and so you're looking for a solution that would give you something that would pick out one of those whole two-parameter family of curves. And so you can, if you have an initial value problem, then those initial conditions would help us, but you can use the boundary value problems to do that. I wouldn't call them parameters. I would call them conditions that would help you find your parameters. I would call like the C1 and C2, those would be like the parameters. All right. So that's just a little glimpse to a boundary value problem. Um, we're focused more on initial value problems. Let's go to our second definition of homogeneous, which is really what the definition of homogeneous is when something's set equal to 0. For all you linear algebra people, a homogeneous differential equation is a differential equation essentially that's set equal to 0. And a non-homogeneous differential equation is a differential equation where the right-hand side is not 0. Well, that's just how we're defining it. We're just looking at linear differential equations right now. Yeah. Yes, it's the same. It's just a different pronunciation. All right. In fact, that's what I used to say, and I'm switching it to homogeneous. It sounds a little more French, doesn't it? My daughter was Joan of Arc today, so I got this French thing going. Now they're having a Renaissance Day at school. Anyways, so the note in the bottom says that if we want to solve a non-homogeneous differential equation, we first need to figure out what the homogeneous differential equation is. The solutions for that would be, and we'll talk about how to build on to solving for a non-homogeneous differential equation. Based on some important principles. I don't think I have any example problems for this. This is just a statement. Let me see. Sorry. I don't know about that. Actually, you guys can figure out what homogeneous and non-homogeneous are, right? Got these two silly little examples. What's the first one? Is the first one homogeneous or non-homogeneous? And this one, it's what? Oh, so all the y's have to be, so that's the other thing about the way this is set up, right? So all the function and its derivative that you're solving for is all on one side. And so any other terms that don't have that would be on the other side. And so if you don't have any other terms that don't have y or y prime or y double prime, and then your right-hand side is going to equal to 0, so that's homogeneous. If for some reason you have some non-y expressions, then you bring that to the other side and bring everything with the y expressions on the left side, everything else on the right, and then in those cases you have a non-homogeneous if you have non-zero. Michael? Yeah, somebody asked that. Actually, it doesn't, but we're going to be focused on just linear equations because it's easier. Okay. Good questions. Anything else? All right. So this note about being able to solve for the homogeneous equation first before solving for the non-homogeneous is based on this idea of a principle called superposition principle. And so in my notes, for some reason, I have some information about some differential operator, but I'm going to skip over that, see if it still works. Yeah, so a lot of theories are gonna just just you wait for all you linear algebra people. All right, superposition. So let's take a look at this principle. It says that if you have solutions to your differential equation, individual solutions like y1, y2, and then you have, in this case, k solutions, then the linear combination, right? Linear combination just means you add them and then you scale or multiply them. So a number times a function, another number times a function, another number times a function. The linear combination of all of those functions, which individually are solutions to your differential equation, if you add them up and then you multiply them by something, then that's also going to be a solution to your differential equation. They're all independent. Well, let's talk about linearly independent later, but the idea is that I can just add them and string them up, or I could just take one of them and multiply it by 15, and it'll still work. So let's take a look at some examples. And again, we're still not solving for any differential equations, but we had an example here in the beginning where we took a look at, this seems to be a simple problem. Let's ignore a lot of this stuff here. And let's just focus on the differential equation and the solution. Okay? So what they're saying here is that e to the x could be a solution to this differential equation. E to the negative x could be a solution to this differential equation. Right? So based on this example, let's check to make sure that these are actually solutions to the differential equation. Let's see. I need the derivative of this and the second derivative of this. So if I put that into here, I have e to the x minus e to the x is equal to 0. So that works, right? Now I need the derivative of y2 to check if y2 works. And I need the second derivative of y2. And then I'll put that into check. We have an e to the negative x, that's y double prime, minus y, original y is e to the negative x, and that's equal to 0. So that also works. Now they say that I can have a linear combination of these two, which is really this. That's about as general linear combination as you can have. But if I just make it up and say 100 e to the x minus 1/5 e to the negative x, I'm just making that up. Then this should also work in a differential equation, right? Let's check. Do we have to? Let's check. So this is 100 e to the x minus 1/5 negative e to the negative x. So that would be a plus. And then I need the second derivative, 100 e to the x plus minus 1/5 e to the negative x. Okay. So now I'll take this and I'll take this and subtract them. y double prime minus y is, well, all this stuff. Seems to be the same, so they should cancel. So it doesn't matter what those constants were. I put 100 and 1/5, but you can put whatever constant you want there. That's what it means to be a linear combination, and it works. So if I have two basic functions that are solutions to a differential equation, then any linear combination of that would work. And the most general linear combination would be just to assign arbitrary constants next to those individual functions. Well, I think that will help us find each individual solution separately. Our goal is probably going to be looking for each of those individual functions separately, and then we string them up with the C's, arbitrary constants, and then we have a general solution. Yeah. So we're gonna hopefully we'll find that out. Skip over differential operators. Say it again. Yes. Yeah. But if what did I just copy? Linear independence. Well, there's some corollaries from the theorem. If you have a set of functions, then a constant times a function is going to be a solution. And the trivial solution is always going to work for the homogeneous differential equation. I don't know what this is doing here. I didn't want to do an example. Yeah, I don't want to do that example. I mean, you can if you want. Okay, go. I lost myself now. I'll say you try. Because I want to get to this next point. So, turns out that functions are actually vectors in a vector space called the vector space of functions. For those people who've studied linear algebra before, we probably look at R2 and have a 2 vector, R3 and have a 3 vector. And so those are the vectors that we are kind of really familiar with. And they live in a vector space called R2 or R3 or Rn, depending on where you are, what dimension you're talking about. But really, functions or continuous functions are vectors that's part of a vector space, and the vector space would be the set of all continuous functions. And it turns out that these vectors, these functions, exist in this vector space, and they follow the same rules as the vectors that we all know from linear algebra. So one of the rules that we're going to talk about, exploit, is the whole idea about linear dependence and independence. The same definition that we have for linear independence with the regular vectors that you know of will work with these vector functions if we take a look at functions as vectors. So if you have a set of functions f1, f2, all the way to fn, you can say that they're linearly dependent if you set them as a linear combination equal to 0, and then you're going to find some constants that are non-zero that would make this equal to 0. And that's how people usually define linear dependence. And then the linear independence is that if they're not linearly dependent, well, they must be independent. So let's take a look at some polynomials. Polynomials can be in their own polynomial space, vector space. And let's say we have functions. Let's say y1 is equal to x, y2, yeah, is equal to x squared. So these are basic polynomials. These are power functions, in fact. And so the question is that, are these two functions independent? And so you would check for independence by setting up your equation c1x plus c2x squared and set it equal to 0 and ask yourself, can I get c1 or c2 to equal something here that would make this thing equal to 0? Other than 0, right? So it turns out that c1 and c2 have to equal to 0 for this thing to work. And we'll keep x as a variable. We're not solving for x, right? We're solving for c1 and c2. So they have to be equal to 0. So this is independent. So these two vectors or these two functions are independent. Now, just as a contrast, let's take a look at an example where you have dependence. y1 is equal to x squared plus x. y2 is equal to x plus 1. And y3 is equal to x squared plus 1. I hope that's that is going to work. Okay. So here I have three functions. I want to know if they're linearly independent or dependent. So we're going to check by multiplying these things by some arbitrary constants, x squared plus x, c2, x plus 1, c3, x squared plus 1. And now, can I find values for C1, C2, and C3 to make this equal to 0? Is it going to work? Which one? So let's change this one. We're just making this up, so. No, it's we're just making it up. What am I trying to do? Oh, so let's backtrack and say this is our new set of functions. Now I want to find out if it's linearly independent. And to do that, I need to write each of these functions with a constant in front of it and add them all up and set it equal to 0. And now the question is, can I solve for C1, C2, and C3 and get answers that are not all equal to 0? So let's see if that'll work. Yeah. Yeah, so we're just going to not plug in values for x. We're just going to let x be variables. And we're focused on solving for C1, C2, and C3 and not x. Correct. So let's see. C1 x squared plus C2x plus C2. Oops, this is C1. C2x plus C2 plus C3 x squared minus C3. Let's combine like terms. C1 plus C3 x squared plus C1 plus C2 x plus C2 minus C3 equal to 0. So these things have to all be equal to 0. C1 plus C3 equal to 0. C1 plus C2 equal to 0. C2 plus, nope, C2 minus C3 equal to 0. And just do some linear algebra. Yeah. X squared, x, and 1 are linearly independent. Yeah. Separately. And yeah, I'm just making things up so that it'll hopefully add up and work out. Is it adding up and working out? I'm worried now. What's C1 equal to? I don't want to solve for this. C1. So C1 equal 1, C2 equals -1, and C3 equals -1. Oh, it just looks like a 2. It's really a 1. Is this going to work? If this is +1, this is -1, and this is -1. Yeah. So we see that CI's are not all 0. So that means these must be dependent. Dependent. So if they are forced to become 0 for this to work, then they're independent. And if you can find them that's not all 0, then they're dependent. As you can see, this is probably not the most efficient way of doing this. So, I mean, this is according to the definition, this should work. So the question is there another way to do this? Well, I wouldn't ask that question if there weren't. So let's find out the other way of doing it. To figure out whether functions are independent or dependent. What? Without the definition. I'm afraid we're not going to get away from linear algebra. I got my underlines here. Hey, this is a cool name. I don't know. I'm not German. Wronskian. Wronskian. What? Oh, it's Armenian? Wow. The Wronskian. So if you have a set of functions Usually we generally would have 2 or 3 functions, but this generalizes to as many functions as you want or need to. If we have a set of functions, then you can write on the first row of a matrix the original functions. The second row would be their derivatives. The third row would be their second derivatives. The fourth row would be their third derivatives, etc. And then what? And then you take the determinant of it. What's a determinant? Yes, it's a matrix determinant. A determinant of a matrix was a determinant is a numerical value that describes a matrix. It's a scalar value for stuff. Scalar. Scratch numerical. It's a scalar value that's one way to describe a matrix. So a matrix is an entity that's a two-dimensional array. A vector is an entity that has a one-dimensional array, or it's a line segment with direction and magnitude, right? And a determinant is a scalar that would be one descriptor of a matrix. It's not necessarily the length of a matrix, because some matrices have determinant 0, and so and it doesn't look like it's 0, but yeah.
Then aren't these functions and multiplying them by each other is not going to give you a scalar?
When we say scalar, we mean not vector and not matrix. Yeah. Yeah, that's a good point. Yeah. Yeah, like in Calc 3, they look at functions and they say it's a scalar function to differentiate from a vector function. So functions can be considered as scalars, but that's not quite. I don't want to talk about it that way because we've just said that we have scalars times a function. So you're right. Yeah. Yeah. So let's just say determinant of 2 by 2 and 3 by 3 matrices. So for a 2 by 2 matrix, sometimes if they don't use the square brackets, if they just use vertical lines, that automatically means determinant, and you don't have to put the DET in the front. I keep always putting a DET in whenever with the determinant, but you'll see in the readings and in a bunch of other math books that if you just see a straight line instead of a square bracket for the matrix or a parentheses, then that straight line means determinant. So the determinant is going to be the product of the diagonals, A times D, that's the diagonal, minus the product of what they call for a 2 by 2 matrix, they call it the wings, B times C. So that's the determinant of a 2 by 2 matrix. Yeah, so determinant of a 3 by 3 matrix can be done in a lot of different ways. The way I'm going to do it will be depending on a 2 by 2 matrix. So determinant of A, B, C, D, E, F, G, H, I. And this process is called expanding on a row or column. And we can expand on any row or any column for that matter. And here how it's going to go. So it's going to be expanding on the first row. We'll take my first element, and then I'm going to multiply by the determinant of the rest of the elements after I cross out the numbers where A, the row and the column where A is. Okay? So after I cross that out, I have EFIH or EFHI. Okay? Now here's the other tricky part. As I expand on my row, the first one in the upper left-hand corner has a positive sign. As I move along a row or a column, my signs are going to alternate. And so I have A was a plus, and then B is a negative, and then when we get to C, it'll be a positive again. So I'll start off with a negative B, and again, I'm going to cross out the row and the column where B is in, and then I'm going to take a look at what I have left. So that's DFGI. The pluses and minuses look like a checkerboard. Those are the signs of the thing. And then so our last one is C, and then our remaining submatrix is DEGH. And with this method, you're going to take a look at now the determinants of each of these, which are 2 by 2 matrices, which is this. Okay? So that's how you guys are gonna find determinants, unless you know how to find it a different way, which is fine, as long as it's correct. Okay? This is how we're going to find determinants, yeah. Because the Wronskian is going to be the condition that we're going to take to make sure that our functions are linearly independent. Like, yeah. Yes. Okay. Now, we had an example. Let's use the example that we had where we found it to be dependent. And then you can check for yourself. Well, actually, the first one is easy. So check e to the x and e to the negative x. Okay. So we say we want the Wronskian of e to the x and e to the negative x, and we write it with the w parentheses and then whatever functions we want to figure out are dependent or independent. So how do we do that? We put the first row to be the functions that we have, and then we take the derivatives of these functions. Right? And then we take the determinant. So this is negative e x e to the negative x minus e to the x e to the negative x. No. So e to the x times e to the negative x, you know what that's equal to? That's equal to 1, right? So minus 1, negative 2, and more importantly, not equal to 0. So what can you say about these two? E to the x and e to the negative x are linearly independent. So we know for our second example that those three functions were dependent, right? Was it x squared plus x plus 1, and x squared minus 1. So let's take the determinant of a 3 by 3 matrix here. We're going to lay out all the functions in the top row. X squared plus x plus 1, x squared minus 1. And then let's take the derivatives. 2x plus 1, 1, 2x. And then one more, 2, 0, 2. Now, in this example where I expanded on row 1, you can really expand on anything. So to take the determinant, expand on any row or column, and what I would like for you to do is take a look at a row or a column that looks like it's going to have nice, easy numbers to deal with. So if I take a look at the second column or the third row, that has a 0, and whenever you have a 0, you really want to take advantage of that. So we're going to expand on row 3 because these are all constants and one of them is 0. Now let's do the expansion. So this is going to be, we need to do that checkerboard thing, check whether we're positive or negative. So this is positive, negative, positive, negative, positive, negative, positive, negative, positive. So I'm expanding on the third row, and now I'll start off with a positive 2. So 2 times, and then I cross out the row and the column. I have x plus 1, x squared minus 1, 1, and 2x. Oh no, just 2x. The pluses and minuses in red are just the signs that I would give when I expand. Yeah. Oh, maybe that's a little confusing. I should circle those. They're not part of the expression. All right, the next one is 0, so it doesn't really matter what happens to the submatrix. And then the last one is a positive 2, and then that crossed out will give me this submatrix, x squared plus x plus 1, 2x plus 1, and 1. Okay, so I have 2x plus 1 times 2x minus 1 times x squared minus 1. Oh, this is so exciting. Lost track of time. So the rest of this, after you work all this stuff out, you should eventually get 0. Spoiler alert, you're going to get 0. For the Ronskin, not your test.